Welcome to Tech Teach.
To be transmitted, data must be transformed to electromagnetic signals. So whenever we are sending a data that is going to be transmitted, then it should be converted to electromagnetic signals. So if it is converted to electromagnetic signals, then only we will be able to transmit to a particular medium, transmission medium. Okay, so that means there is a requirement of data modification or the signal modification, signal transformation we need to do, so that we will be able to modify it to an signal such that it should be able to transmit it through a particular medium. So there is a data that needs to be sent, but that data, once we were to send, that to be sent in the form of electromagnetic signals. Okay, so that's why we will be going with the different types of. So here, so data can be an analog signal or a digital signal. Okay. So both type of signals can be there like analog and digital. So these analog and digital representation can be helpful for identifying a particular data. Okay, so the term analog data refers to information that is continuous. So continuous in the same, it is talking about with respect to time. So with respect to time, uh, data must be continuous. So that will be the analog data. Another one is the digital data. So it refers to the information that has discrete states. Means after a certain time, this states will be having some value. Otherwise, for certain time, it will be having no value, or there will be a sudden change in the value. So then that type of data will be like a digital data will be there. If an analog data is there, it will be continuous with respect to time. So analog data takes on continuous values because it is in the form of continuous. Okay, and digital takes on the discrete values. It will be, if digital data is there, it will be in terms of discrete values. There will be sudden change in between low and high values. And analog data are continuous and takes continuous values, and digital data have discrete states and take discrete values. So if different discrete states are there, then it will be taking the discrete values. So how it is basically represented, we will just go through with some type of examples of different type of signals. So signals can be analog or digital. Analog signals can have an infinite number of values in a range. In a range, it is talking about, suppose a signal is there. So this is with respect to time it is talking about, and this is its value of the signal. So if any signal is there, suppose this is the signal. Okay, suppose like this is a signal. Okay, so for each time duration is starting with 0 to a time duration like any time between this, at certain time it is having a value, fixed value. Okay, and this values are continuous in nature. So if we talk about here to here, there also like infinite values will be there. Infinite values will be there in between this type. Similarly, you can take any time, either smaller or larger. There will be infinite possible values in between this range. So that represents the continuous signal. Okay, so it will be having infinite number of values in a range. That will be the analog signal basically. Similarly, in case of digital signals, can have only a limited number of values into a finite range basically. So whatever the range is there, so if any digital signal is there, so suppose this is the analog signal. Okay, suppose this is the analog signal, but with respect to time, the analog will be having continuous values. But if we talk about the values only at certain points, suppose at 1, this is at 2, 3, it is having 0, again at 4, where suppose some value is there, then again 0, likewise. So these circle values are the only value that is defined into digital signals. In between the first value and the second value, there is no value. That means it is having no value in between these times. So there is a discrete in values. So discrete values are there. They are not continuous. So suppose this is magnitude. Its value is suppose 1 is there and this is 2. So between 1 and 2 there is a gap. So this is having discrete values. These digital signals can have only limited number of values, in a range of time basically. So whatever range, if we talk about, suppose here and here, this is the range. In between this range, number of values are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So means between these times, only 13 number of values are defined. But in analog signals, whatever time range you consider, in between that time range, there will be infinite number of values. So that's why it is called like continuous signals that are analog. If it is limited number of values are there, that will be the digital signals. So the example is here in terms of comparison it is given. Okay, so there is an analog signal, it will be having a continuous value. For each time you can take, there will be infinite values. But in case of digital signals, it is like between this range only one value is there. Okay, so up to here there is only one value. So between here and here only one value is there. Okay, so likewise this is the digital signal basically. So analog signal will be having continuous values, these are the values, continuous values of a signal for each time. But in case of discrete digital signals, it will be having values, but limited values will be there. So this is value, suppose 1 is there, this is suppose it is 2 is there, and this is suppose -1 is there. So likewise 1, 2, 3. Or if we talk about this is as 0, so 1, 2, 3, 4, 5 values are there only in this complete time duration. So this is the basic difference between the analog and digital signals. In data communications, we commonly use periodic analog signals and non-periodic digital signals. So what is its meaning? In case of data communication, if we are using analog signals, then we will be using analog that is periodic. Analog signals like a sine wave is there. So sine wave is an analog signal and it is periodic. Okay. So periodic in the sense it will be repeating its values after a certain time duration. Okay. So from here to here, you can take up to here. This value is repeating again and again. So that means this signal is a periodic signal. When basically we are going to have a data communication, we use non-periodic digital signals. So suppose a digital signal that is previously we have seen, this is the digital signal. Okay, so what it basically represents is, suppose if it is negative, so it will be representing suppose 0. If it is having high value, it will be representing 1. Suppose digital signal is there, that is representing like, suppose it is initially it is 0, then it is 1, then it is 0, then it is 1, then again suppose 0, 0, it will be 0, and then 0, then suppose it is going to be 1 and 1. So it is representing 0, 1, 0, 1, 0, 0, 1, 1. So this is the digital signal basically. So here you can just see, suppose we want to transfer a digital signal, so it's 4 0 1 0 1 0 0 1 1. So it is like, once we are going to use digital signals, it will be a non-periodic. Non-periodic means it will not be repeating its values. So if we are talking about analog signals, we should be having an periodic type of signals. If we talk about the data communication type, okay, if we are sending a data in the form of digital signals, we will be having aperiodic or non-periodic. It's called like aperiodic or non-periodic signal. So digital signals, because based on the data, we will be having different values. So it need not to be a periodic signal. It will not be repeating again and again. The repetition in the sense, whatever suppose we want to send 0 1 1 0. So again after some time 0 0 1 0 will be sent. Again 1 0 0 1 0 will be sent. Again 0 1 0 will be sent. So it has no meaning of sending again 0 1 0 0 1 0 again and again. Okay, in case of digital signal. So that's why digital signals that we will be using will be aperiodic in nature. It will be depending on the data available. It will not be always a periodic in nature. Okay, so that's why it is given like analog signals will be periodic that we will be using in communication, data communication, and digital signals will be in aperiodic type or non-periodic type of signal. So here we will see some of the periodic analog signals and how it basically being represented, what different parameters are there that are being basically used into periodic analog signals. So like we will take into example of sine wave, then what is wavelength, what is time, and what is frequency. Domain analysis, we will see what is composite signals, what is bandwidth. So these are the different parameters that are the points that we will be discussing. Okay. So here the periodic analog signals can be classified as simple or composite. So what is the meaning of simple and composite? So suppose a single sine wave is there. This is single sine wave. So this single sine wave can be represented as the simple periodic analog signal or simple one. If suppose different sine waves with different frequency and amplitude are composed into a single waveform. Suppose this is having one sine wave, another sine wave is like suppose this one. Okay, and the third one is like suppose this one is the third sine wave. So that means if a waveform is there that is constituting of different sine waves, more than one sine wave, then its equivalent representation will be somewhat different. It will not be a sine wave. Okay, so by combining these three, so like here it will be adding the values, then like it will be having some values, random values to, can be suppose this will be the values. After adding all the three signals, suppose the values are likewise. Okay, so if we are going to include more than one sine wave into a single signal, then that will be considered as the composite sine wave signal. Okay, so it has more than one sine wave. So this will be considered as the composite signal. Okay, so here we will be going to see what is the advantage of having a single sine wave and what is the advantage of having a composite sine wave. So whenever we are talking about the signal transmission or the data transmission, because we will be sending different datas at the same time through a single channel. Okay, so that means we will be practically dealing with the composite type of analog signals basically. So that's why there is a requirement of including this simple as well as the composite type of analog waves. So simple periodic analog signal or sine wave cannot be decomposed into simpler signals because this is the single signal, so it cannot be decomposed. If a single sine wave is there, it cannot be decomposed into simpler signals. But a composite periodic signal is there, it's composed of multiple sine waves. It is composed of multiple sine waves, so it can be decomposed. So it can be decomposed into more than one sine wave. So whatever number of sine wave is constituting this composite signal, that number of sine waves it can be decomposed. So decomposed can be done to the composite signals, but not to the simple signals. Okay, so this is the basic idea. We will proceed it further. So this is the simple sine wave. So if a signal is there, so that will be their peak magnitude. If another signal is there that is having lower peak, so this will be the peak value. So one is having higher peak, the above signal, and this is the lower peak amplitude signals. Here the same phase is there and frequency is there. The same phase means starting with the same point. Okay, so that is same phase is there. With respect to origin, the phase is defined. Frequency is in one time duration. Suppose from here to here, suppose it is one second is there. Then in 1 second, how many cycles are there? That is given by the frequency. So here 1, 2, and 3 cycles are there. And here also in between like 1 second, there are 3 cycles of the lower signal. So both are having the 3 cycles, means both are having the same frequency. So its amplitude is changing. The relation between the frequency and period are inverse to each other. So you might be knowing this. Frequency is given by 1 upon the time period, or the time period can be given by 1 upon frequency, inverse to each other. So how it is related? So here two different waveforms are given with different frequency. So how the frequency is basically defined is in one time or 1 second basically. This is 1 second duration is starting with 0 to this point. This is 1 second. Okay. So if this is 1 second, in 1 second, how many cycles or how many periods of this waveform is available, that will be given by the frequency. Okay. So that is like, this is the red portion that is highlighted. This is the one period basically. Similarly, this is the second period, third period. Likewise, there are total 12 periods are there. 12 periods in 1 second. Its meaning is the frequency is 12 hertz. Similarly, in the second one, we can just see that this is the duration of 1 second from starting with here to here. This is the 1 second duration. In 1 second duration, how many periods are there? That means periods in the sense one cycle of the sine wave. So one cycle is starting with here. This is positive and then negative. So this is one cycle. Complete one cycle is there, or one period is there. So this is one period, second period, then third, fourth, fifth, and then sixth. So total 6 periods are there. So 6 periods of this sine wave into 1 second. That means its frequency is given by 6 hertz. So frequency is basically can be given as, this frequency can be given as the number of periods per second. So number of periods per second for a signal, that will be the frequency. Okay, so this is how the frequency is given, and one period or one cycle is given by 1 upon 12. So because 12 is the number of period in 1 second, so how many seconds will be there in one period will be 1 upon 12. So 1 upon 12, this is the 1 upon 12 second. This amount starting with here to here, this is the time of 1 by 12 seconds into one period. So this period will be given by like t. T is the time period, is like time period. If a periodic signal is there that is repeating itself infinitely, so whatever its time period, that is period, that is given by 1 upon the 12, like whatever the frequency. So if frequency is given, we can find out the time period, or if time period is given, we can find out the frequency. So here the power we use at our homes has a frequency of 60 hertz. We already know, like 60 hertz power supply, the AC supply that we basically use in India, that is of 60 hertz. So if 60 hertz the frequency, then the time period will be given by t is equals to 1 upon f, is equals to 1 upon 60. If we divide it, it is like this much second. Or if we multiply it with 10 power 3, that will be represented as millisecond now. So this multiplied by 10 power 3, that will be millisecond, or we can call like 16.6 millisecond. So your frequency is the rate of change with respect to time. So frequency is the rate of change with respect to time. Rate of change with respect to time. So with respect to time, whatever is the change, this frequency. Change, if that change is a short span of time, means high frequency. That means short span of time means time period is less, then the frequency will be high. Similarly, if the time period is long, then the frequency will be low, because with respect to time, the frequency is inversely related to. If signal does not change at all, its frequency is 0. So as in the case of like DC signals or the battery signal is there, that does not change. It is basically constant, not change. That is basically the constant. If not change means its meaning is it's having the frequency of 0 hertz. Hence there is no change in the DC signals or battery signals basically. That is the 0 hertz. Because that will be considered as the 0 frequency if there is no change. If a signal changes instantaneously, its frequency is infinite. If the change is very high, it is suddenly it is at every instant it is changing. That means it is having the frequency of infinite. Okay. So infinite in the sense how it is given. So frequency is given by 1 upon t. So it is saying like t is the change or the period after how much time the signal is basically changing. So it is changing instantaneously in the sense t is equals to 0 is there. If t is equals to 0 is there, in that case, how it will be changing? So for t is equals to 0, the frequency will be given by 1 upon 0, so it will be given by like infinite. So practically it is not possible, but yes, if there is instantaneous change or time period of a signal is 0, then that can be the case. Frequency will be coming out of infinite. Phase describes the position of the waveform relative to time 0. So with respect to time 0 on the axis, how the phase is or how the signal is basically changing, that will be defining the phase. So we will just see here with an example. So 3 different sine waves are given with different phase, but having the same amplitude and frequency. So amplitude means its maximum value and minimum value, maximum value, positive value or peak value will be same for every signal, and also like number of cycles or number of period per second will be the same, then the frequency is same. So here it is same for everyone, but the only difference is the change in phase or basically the phase. Basically that phase starts like at 0. What is the position of this wave, that will be defining the phase. So if it is starting from the time period like time 0 only, so it will be having 0°. If it is starting with maximum value at time 0, maximum peak value, that means this signal has basically shifted likewise. Okay, so shifted 1/4 or whatever is the time period. So time period is supposed t. So t is the time period of one signal. Okay, so it is shifting one portion will be 1/4. So 1/4 is changed. So 1/4 of the time period after taking 1/4 of the time period time, the signal is starting. So this is having a phase of 90 degrees. Similarly, if it is taking the half of the time period, so after half of the time period it is starting, so that will be given by like 118 phase change is there, and this is like 0°. Similarly, if it is suppose changing, the sine wave is likewise. So instead of it starting with 0, then at maximum, then at this position. Okay, now suppose it is starting from here. So this will be considered as like, so previous to that, there are the signals. This is coming out to be 3/4 of the time. So 3/t. So that will be considered as 270° phase is there. Okay. So how it is basically defined? So complete one cycle. Okay. So complete one cycle will be given as 360. So total time is t. So that is given by like 360°. Okay. So in that case, if one time is there, is 360. So similarly, if 1/4 time is there, so 1/4 of the time will be given by like 360 divided by 4. So it is 90°. So if it is like t/2, okay, so t/2 means 360/2. So it is 180°. So likewise, if it is like 3/4 time after it is starting after 3/4 of the time period, so we will be doing the 360 multiplied by 3/4. So it will be coming out to be 270-degree phase. So this is how the phase is defined. The wavelength and period. So if we talk about the transmission of a signal through a medium, a transmission medium, then there will be a wavelength that will be defined. So this is the transmission medium through which the signal is basically transmitting. Okay, so if the signal is transmitting after one time period, okay, so after one time period, this is at time period t. So at time period t, this was the wave. At time t plus 1 or t plus capital T, this is capital T is the time period of the signal. Then after transmitting the same signal through this transmission medium after plus t time, then what is the difference between the one period to this one is coming out to be like wavelength. We'll be considering as the wavelength. What is the wavelength of that signal basically? So this is how the wavelength is going to defined. So this is time and this is the time period. So this time period is time period of one signal or signal that is being transmitted. So one cycle time is will given by the time period. So whatever the difference in between that, so how much length or it is going to travel. So this was the transmission medium starting from here. Okay, so after one time period, so it is starting at t equals to suppose 0 is there, t equal to 0 is there. That means as t equals to 0, the signal is transmitting the first signal. Second signal is transmitting after t time period. So after t time period, this will be the t time period basically. So after t time period, the same signal is again transmitted. So whatever is the extra distance, the next signal will be traveling, that will be given by the wavelength basically. This is the wavelength. Okay, so this is the wavelength. How we need to find out practically the what is the wavelength. In one time period, what is the distance traveled into a medium, that will be the wavelength. So okay, so we can call it like wavelength is the length of distance traveled by a wave into a medium in t time, where t will be the time period of what is the meaning of time domain and frequency domain. So if it is time domain means change in the amplitude of the signal with respect to time will be given by the time domain. The same is like frequency domain means change in the amplitude or the representation of the amplitude of a signal with respect to frequency. So that means here with respect to time, how the signal is changing. So if it is a normal sine wave, it is having the peak value 5. So it will be going to peak value 5, and then in the negative direction, it will be going to -5. Then again going to +5, -5. Likewise, it will be changing, and its frequency is 6. Means up to in 1 second, it will be having 6 cycles. So one cycle, second cycle, third, fourth, fifth, and sixth. 6 cycles will there or 6 periods will there into 1 second. So this is equivalent to 1 second. So in 1 second, 6. Its meaning is in 1 second, it will be having 6 periods or cycles basically of this sine wave. This is in terms of time representation. Now it is in frequency. So because it is having a frequency of 6 hertz and we want to represent its change in amplitude with respect to frequency. So it is having a frequency of 6 hertz means in frequency domain at 6 hertz only. So this is the 6 hertz at this hertz only, 6 hertz only. The value of this signal will be like the 5. So 5 is the amplitude. It will be having the amplitude same 5, but it will be representing only at 6 hertz frequency. All other hertz will be remaining 0. So a single sine wave can be represented in time domain as this, varying with respect to time, but with respect to frequency, it is having a fixed frequency of 6 hertz. So at 6 hertz only, there will be a peak value that is 5 volts. Otherwise, for other frequencies, the peak value will be 0. So this is how the basic representation of a signal into time domain and frequency domain. Okay, so I hope you have got the point. So here the peak is 5 volt and frequency is 6 hertz. So at 6 hertz only there will be a peak of 5 volt. Case of frequency domain. A complete sine wave in time domain can be represented by one single spike in the frequency domain. So we can conclude from the previous diagram, like complete sine wave that is there represented here, having a representation with respect to time, that is having the continuous keep on at infinite time. The similar structure will be there for time domain. But in frequency domain, the same signal, the sine wave, can be represented as a single spike at frequency 6 hertz. So time domain and frequency domain, the representation of 3 sine waves is given. So 3 sine waves. So 1 sine wave, 2 and 3 sine waves. So 1 sine wave is having the frequency of 0 hertz. So frequency of 0 hertz and having an amplitude of 15. So this is the 0 hertz means it will be a constant. There is no change. So it is a sine wave with 0 hertz frequency. So it will be with 15 volt peak and 0 hertz. So this is having the frequency of 0 hertz. Next is 8. 8 means into 1 second. This is the 1 second. Into 1 second, there will be 8 cycles or 8 periods will be there. So this one is having the 8 hertz frequency. This is having the frequency 0 and it is having the amplitude of 10. Your amplitude is 10. Next is having 16 as the frequency. So this green one is having the frequency of 16 hertz. Okay, means 16 cycles are there or 16 periods are there into 1 second. To 1 second, green signal is having 16 cycles. So it will be having the 16 hertz as the frequency and amplitude is 5. So these 3 sine waves are composed into a single, like it is transmitted through a medium. Suppose there is a transmission medium, through that these 3 signals are transmitted at the same time. So how we can decompose it or how we can identify it? So for that, or to decompose these signals, we need the frequency. Okay, so if we talk about this frequency, so similar, these signals can be converted to a frequency domain analysis. So in frequency domain, at 0 frequency, we will be having a peak of 15 volt. Okay, similarly at 8, because 8 is having another signal, so at 8 we will be having a peak of 10. So at 8 hertz, we will be having a magnitude of 10 volt. Similarly at 16, we will be having a magnitude of 5. So this is the 5. So that means if 3 signals are transmitted at the same through the same channel, through the same cable, we can identify it easily with the help of frequency domain. So this frequency domain analysis is helpful for identifying. That's why what we do is in radio, what we do, we tune to different frequencies. So that means at different frequencies. Suppose if the frequency is 8 hertz, if the frequency is 8 hertz, we will be able to listen to this signal that is having the magnitude 10 volt. If suppose we are switching at 5 hertz, at 5 hertz there is no signal, so it will be 0. So no signal will be received. So in AM receivers, we basically, or in TV receivers also, once we change the frequency or we change the channel, so that change in channel is nothing but the change in frequency. We change the frequency. So at that particular frequency, if there is any signal, means there will be an amplitude of that signal. So that amplitude is basically detected. So that's how the frequency or the channel changing, or in radio we basically change the frequency and we get the signal. If a single frequency sine wave is not useful in data communication. So if a single frequency is there, we will be not using that. So basically, so multiple frequencies are used. Okay, so that's why single sine wave is not useful in data communication. We need to send a composite signal. So composite signal will be constituting of more than one sine wave. Next is like if the composite signals is periodic. So here it is. If the composite signal is periodic, the decomposition gives a series of signals with discrete frequencies. 3.9 shows a periodic composite signal with frequency f. So that means the periodic composite signal means this signal is basically a periodic signal because it is repeating itself. So this is like from here to here, there is one cycle. Similarly, this is another cycle or another period. So there is a periodic signal. Okay. So this is from here to here, and again from here to here. This is repeating again and again. So that's really like a periodic composite signal will be here. If we decompose it, so decomposition of composite periodic signal is like here. So if we decompose it, we will be getting three different signals, sine waves with frequency f. Suppose one is having the frequency f. So suppose red one is having frequency f, then the blue one is having the frequency of 3f, means three times it is repeating. So into one cycle, this is the one cycle of the red one. Then blue one is going for three times, 1, 2, and 3. Three periods are there into one period of the frequency. So it is having 3f frequency. Similarly, the black one is going for 9 times into one period of this red signal. 9 times it is repeating, so it will be having frequency of 9f. So means this signal that is looking here or in this slide basically. So this is composed of three different signals of different frequencies. And if we represent this into the frequency domain, it will be coming out like at frequency f, we will be having a magnitude of this that is having high magnitude. Okay, so A1 we will call it. Then this is blue one is A2. Then black one is A3. Okay, so it will be like having a magnitude of A1. The blue one will be having a magnitude of A2 at 3f frequency. Similarly, the black one will be having a smaller magnitude and at 9f frequency. This is A3. So this is how a composite signal is look like. And if it is a periodic, we can represent it in terms of three different signals. And after decomposing, we will be getting the three different frequency components into the frequency domain. Okay, so this is not the time domain. This should be frequency basically. It should be f. So frequency domain it is talking about. Okay, so this is frequency domain signal, not the time. So this is another signal, but here it is a non-periodic signal. Okay, so figure 3.11 shows a non-periodic composite signal. So it is having a non-periodic composite signal. It can be the signal created by a microphone or a telephone set when a word or two is pronounced. So either we are pronouncing one word or two word, this type of signal will be generated through the microphone. So this is like a, it is not a periodic, it is a non-periodic signal, or this is a composite signal with no similar repetition in the pattern. Okay, so it is non-periodic. So if it is non-periodic in time domain, if this is the signal, similarly, if we convert it into frequency domain, we will be converting it such that its frequency will not be a single frequency. It will be having a frequency with its magnitude will be changing with respect to the frequency. That means it is now looking like a continuous signal. It is here continuous in nature. So that means if any signal is there, if it is aperiodic or non-periodic, its frequency domain will be a continuous type of signal. So this its meaning is that we have uh, declared into an statement. If an aperiodic type of composite signal is there, then it will be having a, in frequency domain, it will be having a continuous type of behavior. It will not be having a single magnitude at a particular frequency, but it will be taking all the frequencies, and this 4 kilohertz up to here, that will be given by like the maximum frequency to which its magnitudes are defined. If an periodic composite signals are there, then its frequency domain representation will be in discrete form. Okay, so this is periodic. So if periodic signal is there, its frequency domain will be, in time domain it is periodic, but in frequency domain it will be discrete. And its other to it is, in time domain it is aperiodic, then in frequency domain it is continuous in frequency domain. So the bandwidth of a composite signal is the difference between the highest and the lowest frequency contained in that. So its meaning is like, suppose this is the bandwidth. Okay, so this is two signals. One is for periodic signal and another one is non-periodic signal. If it is periodic signal, for a particular frequency, there will be amplitude. For different frequencies, there will be an amplitude. But the bandwidth will be defined as the maximum frequency into this frequency domain. Maximum frequency is 5000 and the minimum frequency. Difference of maximum and minimum frequency will be given by the bandwidth. So this is the complete bandwidth of the signal. Okay. So similarly, in case of aperiodic type of signal, the complete bandwidth will be given by again here between the maximum frequency and the minimum frequency. Okay, so that will be maximum minus minimum will be 4000 hertz will be the bandwidth. But in case of periodic signal, the frequency components will be discrete. So they are discrete in nature that we have just seen. And if it is aperiodic, it will be having a continuous type of nature. So bandwidth will be the highest frequency minus the lowest frequency. That is the bandwidth.